Hello everyone, and welcome back for our first lecture of the semester. Today we'll be going over an introduction to geology and Earth's interior. So what is geology? Geology is defined as the science that deals with the Earth's physical structure and substance, its history, and the processes that act on it. So what is it made out of? How did it get there? Or what's there and how did it get there? And why should we care about geology? Well, first and foremost, Earth in and of itself can be considered a limited resource. So everything that we have is made or synthesized from Earth material if it's not a raw Earth material already. If you look around you, you might see the glass in your window, which is made of quartz and a couple of other things. It's a raw earth material. If you are drinking coffee out of a mug, there's likely clay in it, clay from dirt. And then you're watching this on an electronic device, whether that's a computer or a phone or tablet, whatever it might be, that has conductive material in it, or conductive metals, which are from mineral ores. So being able to understand where we get all of these things from allows us to have a better understanding of the world around us and how it actually works outside of us specifically, so we can think of things in terms outside of consumption as well. And then understanding how all of these things got to be here can help us understand how to make more of it if we need to, how to limit ourselves if we need to, and then how to predict where things are going in the future based on how we've gotten to the point that we're at now, which can help us to keep our home livable not just for us, but for any other living thing. So what is a geologist? A geologist is a person who uses the scientific method to study the physical and chemical processes of the Earth. This includes the atmosphere and the hydrosphere on top of the geosphere. And then we'll also look at the interactions that the Earth's components, the geosphere, hydrosphere, and atmosphere have with the biosphere, so all living things as well. So we have Earth, wind, water, and life. Fire, too, we can throw that in there if you want to count lava or just general chemical reactions. So be it that this encompasses a lot of different components of the Earth, there are a lot of different kinds of geologists. For example, we can have hydrogeologists, so that's a water-related geologist. This is primarily what I do. So I work at the Michigan Geological Survey in a project concerning contamination in groundwater. I also look at a lot of surface water interactions and flow, things like that. We also have remote sensing, which is a relatively new sector of geology. This is the use of unmanned aerial vehicles or drones to capture large, high-quality, high-quantity data sets, such as temperature data, elevation data, just straight raw images, and a few other things in order to build a model or a picture or a timeline, anything like that. And then we can have sedimentologists and stratigraphers. Sedimentologists deal with sediment, and stratigraphers deal with stratigraphy. Stratigraphy is the ordering or layering of different types of rocks in the subsurface, and these people commonly work in oil and gas identification, in those types of resources. That has a lot of overlap with geophysics as well. And the name of the game with geophysics is to use a number of different tools or surveys available to create an image or picture of the subsurface. So we don't know necessarily what's directly below us unless we dig into it, which, depending on how deep you need information for, can be really expensive. So in geophysics, we have some instruments that allow us to simply walk or fly over a piece of earth and image what might be below. And oftentimes you'll have multiple images from multiple different surveys that piece together into something that can actually give you relevant information. Geochemists will commonly work with hydrogeologists. A lot of geochemistry relates to either reactions within volcanic systems or in groundwater contamination cases. And then some of you might have heard of a paleontologist before. These are like the fun geologists because they get to study dinosaurs, although I think that hydrogeology is fun as well. But paleontologists know a lot about fossils in general. Only a small portion of that is actually dinosaurs. You'll find that most fossils are actually plant or microorganism and sea life oriented, so a lot of corals and things like that. But dinosaurs too, paleontologists are the people for that. The list goes on. Geobiologists, you can probably guess what it is that they work on. Economic geologists, anything that we can exploit for profit. So that would be like the gold or silver, any metals, any precious gems, diamonds, sapphires, rubies, things like that. Oceanography, ocean geochronology, that is geologic timeline is what that really stands for. Volcanologists, volcanoes. And then we also have a few different sectors that are geology adjacent but not quite geology. So an example of that would be environmental consultants. Environmental consultants are usually called in terms of a land transaction to ensure that that piece of property is environmentally sound, you're able to build on it, it can withstand certain environmental conditions, it can support the weight of whatever you're trying to build, there's no existing contamination that may result in a later lawsuit that you would be found responsible for, even if it was the previous company that owned that land. Anything like that, that's where environmental consultants would be called in. They also might do some of the cleanup job as well. And then GIS specialists are another example of something that is geology adjacent. So GIS stands for Geographic Information Systems, and that has some overlap with remote sensing. But really with that, it's being able to take geologic data and create a map or a visual to help us better understand whatever question it is that we're trying to answer. Because a picture can speak 1,000 words. So as you can see, there's a lot of overlap and a lot of options within this. Now, all geologists, geoscientists, or scientists in general use the scientific method. And you guys have probably heard some simplified versions of this before in your high school science classes. This should look familiar to you. You make an observation, you have a question based on that observation, you do a little bit more digging, you come up with a hypothesis to test, you come up with a way to test that hypothesis, you gather your evidence, and then based on that evidence you will make a conclusion that is in either in support of your hypothesis or rejects your hypothesis, and then you will probably circle back and edit your hypothesis based on that, and then retest it again, and so on and so forth. So the only problem I have with the scientific method is how it is sometimes portrayed in education. I didn't find the scientific method interesting until probably halfway through my undergrad. I found that in any class that I had before where we were learning the scientific method, it was often underwhelming or perhaps even boring. And that's not actually the case. The scientific method can be really exciting. It can be an extremely useful tool that can really produce a lot of cool things. So I have a video for you guys today that I think is hands down the best representation I've ever seen for the scientific method in terms of making it appealing and exciting to people who don't use it within their daily and understand the power of the scientific method. Quick disclaimer, it does have a bit of profane language in it, so if you feel that might make you uncomfortable or offended, you don't have to watch it, but I would like you to watch it because it is really fun and it'll be an opportunity to learn something. And you're all adults, so I trust that you can handle it. So let's jump over to that.
It's funny, isn't it? We got all of this technology, we got all of these clever machines, but if anyone actually asks, like, how does any of it work? At all. Often the best reply you'll generally get is, yeah, well, probably someone built a box and a wizard spluffed in it, and now it's magic, and that's how technology works. Everything's just made of wizard jizz. And that's cool, but yeah, I just want to put a bit of an alternate answer out there that, like, yeah, technology is really complex, and the world is really complex, but overall, as it happens, actually, the world isn't wizard jizz, technology's not magic, it's just scientists on acid or applied mathematics. And every piece of technology, from satellites to shoes, started in someone's fucking head. For example, segways, not magic, Physicola, not magic, spacey science place, not magic, magic marker, not magic. It all just relies on foundational physical principles, which we'll briefly discuss now. Hey, this sure keeps time good, right? Is it clockwork or what? Is it just tiny dragons all tapping their talons to EDM? No, it's quartz. And we know if you electrify quartz, it puts out regular vibrations. And we know 32,768 of these vibrations is a second. So if you build a circuit that counts those vibrations, you can keep accurate time. And you just multiply these together until you get hours, days, and years. All thanks to little white crystals that aren't magic. Hey, not all that shabby. Is this some kind of wizardry? Nope, just good fucking science and piezoelectricity. Or, yeah, computers. That has to be magic, right? No. Get sand, purify sand, make silicon ingot, make them wafer thin, do some fancy ion shit, then etching, electroplating, layering and stuff. And now what you've got is a little slab of silicon packed with transistors, which are really just tiny little electricity gates. Then you put them all together in such a way that they form an electronic mind, consisting usually of stuff what goes in, control thing, thinking thing, stuff what remembers shit, and stuff what comes out. A computer is just a little prison for electrons where we train them to solve problems really quickly. And this all relies on the principles of subatomic physics, meaning that the most common use of quantum mechanics in the 21st century is undeniably, most likely, demonstrably, pornography. How does that fly? It's simple, right? Air under wings makes a wing glide, right? Throw in a big fucking spinning thing, right? And if not, maybe some wizardry? No. Flight's a result of a difference in pressure above the wing versus below the wing. And the cool thing is that if you make sure the pressure is higher below the wing than above, then low, yo, that's flight, right? Yeah, also, what the hell is an engine? Well, internal combustion is essentially the process of turning fuel into motion using fucking explosions. In a 4-stroke engine, gas and air go into the engine, and the gas and air is squeezed into an itty-bitty space, a little spark starts a little explosion, forcing the piston to move, then the excess gas is released, and that energy is turned into rotational motion using a crankshaft. And this is generally thanks to gasoline, which is in turn thanks to dead plants from swamps millions of years ago, not dinosaurs, further illustrating that, like, the world isn't wizard jizz, just weird and prohibitive, and really technology is just nature we taught to do cool tricks. And to be honest, can you imagine how utterly miserable life was before we got around to using the scientific method? What's the meaning of life? And hey, why does my butt hurt? Just shut up, invent fire, and get the fuck in the hot butt. Then die prematurely from an easily curable infection. Got a problem? Tough luck, baby. Natural selection. Complex is not a synonym for magic. Everything works somehow. Like a radio. What kind of Harry Potter shit is that? Well, first of all, just imagine the universe is made of interactions, because it is. And one of them is electromagnetism. And what radio is a certain wavelength of that. And if you vary electric current through a wire, you can create vibrations in the electromagnetic field. And if you have something that can pick it up on the other end and turn those waves back into sound, well, that's that. And those are just physical technologies. What about language? Well, currently there's about 7,000 spoken languages in the world. Some of them use grammatical gender, some don't, some are alphabetic, some are pictographic. But the one thing they all have in common is that if you learn one, you can read people's fucking minds. And this technology took thousands of years to build, and is basically the reason we have modern civilization. And it's not magic. Most language processing takes place in the cerebral cortex, we think. Adult native speakers usually know about 20,000 to 35,000 words, but there's plenty of people who speak multiple languages, so closer to 60,000 words or more. And did we find language at the top of a mountain or in a drawer or some shit? Oh no, clever dead people gave it to us. And talking of dead people, the difference between our ancestors and us, well, mainly reason and rationality. Look, there's a good story about Descartes. He was one of the fathers of the scientific method, basically. And one night he had a bunch of wacky dreams, and in one of them an angel came to him, apparently, and said, "The conquest of nature is to be achieved through number and measure, and that, surely, has to be one of, if not the most powerful ideas we've ever had. Scientific objectivity. Nature can be understood using mathematics, then controlled using technology. And as long as we remember that the world isn't in our heads, that the universe has a character, well, there may be no limit to what we'll one day be capable of with technology." Rationality is absurdly powerful. It's the reason we're not sitting around in our own excrement. It's the reason the average high schooler knows more about the world than the smartest human did not a few hundred years ago. It's the reason lots of us are living better than every emperor in history. And Jesus Christ, look what we've done already. Antibiotics, or moldy bread in essence, has probably saved about 200 million lives since it was discovered. Your phone has more computing power than all of the computers that NASA used to send humans to the moon. And scientists are now using lasers to listen to black hole collisions billions of years ago via distortions they left behind in the very fabric of fucking space-time itself. Wizards and witches do exist, and they cast spells called research, usually abusing a magic potion called coffee. And if we don't know everything yet, well, better to have questions you can't answer than answers you can't question, don't you think? And furthermore, man, I don't know if we mentioned this, but the world isn't wizards, maths is where nature lives. Say, who got us to the moon? Was it witches or physicists? And if we met aliens, well hey, that'd be salient, but they'd still use technology, science and astronomy. We most likely weren't dreamt up by Zeus in his chariot. We started out as slime and a fucking precariat. The world is complex, but when you really look into it, even biology isn't magic. Not really. Abrupt ending so we can lead into the next musical section. You know...
Okay, so there's a bit more to that, but you guys can feel free to watch the rest of it on your own time. The link is there for you. I think there's also a part 2 to it, but I hope that made you at least a little bit more excited about the scientific method than previous classes have, and that you learned a little something from it, maybe something fun to share with your friends or family, anything like that. So now's a good time to pause. If you'd like to pause and get up and walk around, stretch your legs, get some water, do whatever before we get into Earth's interior. So I'll give it a couple seconds for you guys to pause and resume if you'd like. Okay, so the figure that we have here shows probably what you've seen before as the interior structure of the Earth, consisting of 4 layers. Perhaps even the models that you've seen before only have 3. So the crust, the mantle, and the core. Here we have the crust, mantle, outer core, and inner core. And this is true, this is accurate, but it is a simplified version of what we actually have. So before we get into the inner workings of that, first we need to establish the composition of the Earth. And what many people don't realize is that the vast majority of the Earth is comprised of just 4 main elements. The number 1 being iron, and that's what makes up the majority of the core of the Earth as well, which is what gives it its high ranking of 35% of Earth's composition. And second, we have oxygen at 30%, then silicon at 15%, and magnesium at 10%, leaving literally everything else that we have to the final 10% of that share, most of which is in the outermost layer of the Earth, the crust, which makes sense because we have access to those, and that's how we use it to make all of our things. You'll find that with increasing depth to the center of the Earth, there is decreasing variability in elements. So we have a wider range of things available to us at the surface where we live, and only really 2 things, iron and nickel, in Earth's core. And elements are our building blocks of everything. One tier up from that, so to speak, is minerals, which are inorganic crystalline solids that combine to make rocks. So in most cases it's inorganic. There's different criteria that make up a mineral, and we do have some biogenic minerals, but for the most part a mineral is something that is made up of a specific formula of elements that is only made as a new substance, so cooling from magma or lava. Some rocks can also result from the cooling of magma or lava, which we'll get into in our igneous chapter. There are 3 types of rocks, or 3 general categories of rocks. Igneous, which is volcanically related or magmatically related. Fun fact, the difference between lava and magma is that lava is when it's on the surface. So if you see it flowing out of a volcano, it's lava, but it's still within the volcano or directly below the volcano, then it's technically magma. And any number of minerals can combine to make any rock. So minerals are the building blocks of rocks. We can also get glasses, which are cases in which lava cooled too quickly for the atoms to link up and make bonds and create a structure. So we end up with a sort of hectic array of molecules frozen in time, and that's how we end up with volcanic glass, referred to as obsidian. We can then break down rocks into sediments. So all sediment is just very fine, broken up rock into grains and powders, mixed in with organic compounds, carbon-based substances such as wood, peat, coal, bacteria, lots of dead bacteria, so on and so forth, oil, and water. So here we have a simplified model of a slice of the earth cutting into the surface down to the core. So it's fining towards the point, with the core being this final point. So at the uppermost surface we have the crust, and below that the mantle, and then below that the core of the earth. Now the surface of the earth, or the crust, is divided into sections called tectonic plates, and these interact with each other by either sliding past each other, bumping into each other, or moving away from each other. And these plates move at a rate of about 2 centimeters per year or so. So we're actively moving here on the North American plate. There are 12 plates around the earth, 12 major plates, and then a bunch of smaller ones. And it will be either an oceanic crust plate or a continental crust plate. Those are the two different types of crusts that we have, oceanic and continental. And you can probably guess what the differentiator between those two are. Oceanic crust is where ocean is, continental crust is where continents are, generally speaking. And as shown in this diagram, continental crust is on average about 30 kilometers in thickness or in depth, and oceanic crust is comparatively much thinner at about an average of 8 kilometers. Now this makes sense because in order for continents to be above the ocean and stick out of the ocean for us to be on, it has to be thicker than oceanic crust, right? And oceanic crust is also much younger than continental crust because oceanic crust is where new crust originates. And continental crust is much older, it's had time to build up and become thicker. Below the continental and oceanic crust, the crust on whole, is the mantle. This goes down to a depth of about 2,900 kilometers, where we then encounter the interface of the core, and the outer core, at that same depth of 2,900 kilometers, and then the center of the Earth is at a depth of about 6,378 kilometers. Now, how we define Earth's layering is by 3 essential parameters. 1, composition, what's it made out of, or the chemistry of it. 2, the behavior, is it soft, is it hard and brittle, is it a liquid, and its physical properties, namely velocity and density. So to dive a bit deeper into the Earth's composition, we'll start with continental crust. And continental crust is made up of what we call felsic rocks. Felsic rocks are described easily by their color. So they have a high silica content of about 65 to 70%, which appears normally as a very light coloration, white, light pink, light gray, those for the most part. And then oceanic crust is on the opposite side of that spectrum with mafic rocks, which are alternatively rich in magnesium and iron. These are heavy and dense elements. That's why when you go to the gym, they say you're pumping iron. It's heavy, it's dense, and it has a much lower silica content than felsic rocks at about 50%. Then we can consider the mantle, which is made up of ultramafic rocks, which is just more mafic rocks, which have a similar chemical composition. They are also rich in magnesium and iron, but they have an even lower silica content, which in turn means they have an even higher magnesium and iron content, which means that it is heavier and more dense. And then lastly, the core is made up of an iron-nickel alloy. That's both the outer and the inner core. They have the same composition. So revisiting that same diagram, I've added in the compositions on here. For continental crust, those felsic rocks, usually granites or granodiorite. You'll get to see these when we get to our rock labs. Next week we'll start with our first in-person lab on minerals. Oceanic crust is primarily basalt. The mantle is primarily peridotite. And then the core, again, iron-nickel alloy. The other thing that I have on here is their average density. So the exact numbers aren't too important, but what I want you guys to know about these is that notice the oceanic crust and the continental crust, their densities are not that different from each other. Oceanic crust has a density of about 2.9 grams per cubic centimeter, while continental crust has an average density of 2.7 grams per cubic centimeter. Pretty close to each other, although oceanic crust is more dense than continental crust, and that makes sense because it's made of mafic rock rather than felsic rock, and the mafic rock has heavier and denser elements, or is higher in content of those, with magnesium and iron. Then if we look at the mantle, slightly higher density of 3.3 grams per cubic centimeter. That makes sense because it's ultramafic, right? So even more of those heavy elements, magnesium and iron. But then if we look at the core, that's a huge jump to make from 3.3 grams per cubic centimeter up to 13.8 grams per cubic centimeter. And that's because it's almost entirely nickel, iron and nickel. And those are extremely heavy and dense elements. So to build on the qualifications or definitions of continental and oceanic crust, we're going to further consider their densities. Now, some of you may have boiled water for pasta in the past and put a little bit of olive oil in there. If you haven't, putting a little bit of olive oil or a different kind of oil in your boiling water for pasta will help the noodles to not stick to each other, because the water becomes saturated in starch when the pasta cooks, which is why you can take a couple spoonfuls of your pasta water that you boiled in and add it to your sauce if you want to thicken the sauce rather than adding cornstarch, because the pasta already has starch in it, and the starch is what provides a thickener. Anyways, when you put the olive oil into the boiling water or water at room temperature, the oil will float in little globules on top of the water, and that's because oil is less dense than water. To continue with this analogy, we can compare the continental crust to the oil in this case. It is less dense than oceanic crust, and the oceanic crust to the water, it is more dense than continental crust. So, mind you, when we have these interactions between oceanic crust and continental crust, if they come together and collide, the more dense material, the oceanic crust, will then subduct or go underneath the oceanic crust. Now, this isn't a complete encompassing, this is just a tail bit of it. And when this happens, we end up with a trench in between those, because the oceanic crust is more dense and it subducts underneath the continental crust. So that diagram is, again, another simplified version of the interior of the Earth. So we can build on top of this, and at the outermost layer of the Earth, we have what is referred to as the lithosphere. And the lithosphere encompasses both the continental and oceanic crust. It's the whole crust of the Earth, plus the uppermost mantle. So the part of the mantle where we have direct contact with the crust is nearly frozen solid because there's so much heat below that, but that just little part of the mantle that's touching the cool crust ends up getting frozen, so that part of the mantle is actually hard and rigid, just as the crust is. So remember that we also group Earth's layers by their physical properties or their behavior. So the lithosphere groups the uppermost mantle and the oceanic and continental crust together because they are all rigid, they're all brittle. And that's why the tectonic plates actually go down to a depth encompassing the lithosphere. So the tectonic plates are made up of both crust and uppermost mantle, or in one word, the lithosphere. And that goes down to a depth of about 150 kilometers or so. Directly underneath that, we have another part of the upper mantle referred to as the asthenosphere. And astheno, it means in Greek, is weak or soft, not hardy. And that's because the asthenosphere is the part of the mantle underneath the lithosphere that is malleable, not flowing in the way of, say, like a running river, but it can flow in the sense of perhaps comparatively to honey that you had in the fridge. So nearly solid, but still can move somewhat. And that's what allows those plates to move on top of the mantle. Below that, the lower mantle is actually solid rock for the majority of the depth, with exception to the middle mantle where there's a combination of heat and pressure that allows it to also flow in a similar way to the asthenosphere, but not quite as flowing as the asthenosphere. So maybe if you had the honey in the fridge just a little bit longer. And the asthenosphere in part flows because of the heat from underneath, but also the overlying pressure or weight of the lithosphere sitting on top of it. Then moving down into the outer core is liquid and the inner core is solid. This is just a restatement of what I went over. This is just so it's in words for when you study later. Revisiting the physical properties, again, lithosphere, hard solid, asthenosphere, soft solid. I'm repeating this and have it in here a lot because this is one of the main takeaways that I want you guys to get from this. And then we have the lower mantle, which is mostly hard solid, outer core, liquid, inner core, hard solid. That's going to be on a test. So when we put these together, again, I'm hammering this into your mind because you need to know this. The lithosphere here, notice the line for that goes past the depth of where the crust stops, the continental crust and the oceanic crust. And why? That's because it encompasses the uppermost mantle as well. As far as these depths go, I want you guys to be aware of their relative thicknesses to each other. So you'll need to know that the continental crust is thicker than the oceanic crust, and the mantle is slightly thinner than the outer core, so on and so forth, just relative to each other. Now, here's another visual for you with the lithosphere and the asthenosphere. So again, that's where we go from crust and uppermost mantle rigid portion to upper mantle malleable portion, the asthenosphere, where it behaves plastically, which is why it says plastic there. The line that separates these two is the Moravec discontinuity, and its discontinuity refers to a discontinuing velocity of energy released from earthquakes, which I'll develop on in a minute here. But the velocity changes or discontinues at that point because there's a change in the behavior of the medium that it's traveling through. We the geologists fondly refer to this discontinuity as the MOHO, so that's what you guys can remember it as well. Now, the mantle actually makes up the majority of Earth's volume, making up 82% of the overall volume. Again, that's an ultramafic composition, primarily peridotite. And mind you, earlier I said a certain section of the mantle is flowable or malleable. That's at a depth of below 100 to 150 kilometers each. And that's primarily from heat that it's able to do that. So I want you guys to think of your convection oven at home. How does a convection oven work? Well, you have a heating element, and then you have your food that you're putting in there, and air will circulate within that oven or convect within that oven. So air is passing by the heating element and heating up, and then it circles past that heating element to your food. As it's passing around the food, it transfers that heat or that energy to your food, cooking your food, and then it flows back. It's cooled now because it's transferred its heat to your food, back to the heating element where it is reheated, and the process continues. And those are convection cells. It's air convection cells. Well, we have something similar happening in the mantle. So we can consider the core of the Earth as sort of our heating element of our Earth oven, and the crust as our food. So you guys have also probably heard in safety training from kindergarten on that when you have a fire in your house, hot air will rise. So you want to crawl and stay low to the ground if you can, so that way you're not breathing in the smoke and you're also not getting too hot yourself. Okay, just a short pause. That tapping in the background should be done now. So where were we here? So we have these convection cells happening in the mantle, where our outer core can act as sort of our heating element, and the crust will act as our food. And we know that hot rises and cool sinks from our fire safety training, right? So we have part of the mantle that is passing by our heating element, the outer core. It heats up, it rises, and as it comes into contact with the cooler part of the lithosphere, it will begin to cool, and then as it cools, it sinks back down, and the process continues, giving us these convection cells. And these convection cells they're the major part of what drives the movement of tectonic plates. We also have convection cells within Earth's liquid outer core. The special part of the core's convection currents, however, is that this is what generates Earth's magnetic field. Earth can be considered as one giant magnet, and our north and south magnetic poles loosely line up with our geographic north and south poles. It's a little bit off by, I think it's about 3 degrees. And that's because our north and south magnetic poles rotate some tens of thousands of years or so. Right now they're aligned so that north is north and south is south, but that flip-flops now and then. And our magnetic field stretches all the way into space, which is pictured in this figure here. The sun is this yellow portion, or the sun's radiation is this yellow portion off to the side. And the outer edge of our magnetic field is this red line, which we would call the Van Allen belt. So the Van Allen belt, or Van Allen belts, is the outermost portion of our magnetic field, the reach of it, where it collides with the sun's radiation, or high energy solar radiation, otherwise known as solar winds. And this is what keeps us from experiencing too much radiation from the sun. This protects us from too much of that coming through to where the Earth is not livable. So we have sort of a multi-tiered protection system here on Earth from the sun's radiation, both the Van Allen belt and our atmosphere. However, occasionally some of the high energy ions or solar winds will break through the Van Allen belt, and when that happens, we get aurora borealis. And when those ions or high energy radiation breaks through the Van Allen belt, it is then drawn into our magnetic poles. This is why we get better views or can only see the aurora borealis closer to the poles. I believe Michigan's still in the window sometimes, but when you get into like Iceland or Greenland territory, then you've got a great view. So how do we know that any of this is true anyways? Well, the short answer and the primary answer is seismic data, or data from earthquakes. When an earthquake occurs, it sends out different types of energetic waves. These are P waves and S waves. These waves have the ability to travel through different media, and they will either reflect or refract, those two types of interactions, depending on what material it is that they're interacting with. And we can use this to create an image of the Earth's interior. So we'll start with P waves, and P waves are able to pass through both solids and liquids. So a earthquake will generate somewhat of a semicircle shaped energy wave. So some of it will simply stay within the upper portion of the Earth and exit out the crust, and that doesn't give us a whole lot of data. What becomes quite relevant to us is when these reach the depth of the outer core, the liquid outer core, and when it goes from being in that solid portion of the Earth to encountering the liquid portion of the Earth, it will change velocity because we have a change in density. So dense materials are harder to pass through. Think about swimming through a pool and then immediately swimming through a pool filled with pudding. Pudding's more dense than the water, so you're going to be moving a lot slower even if you're exerting the same amount of energy. Same thing happens when it reaches the solid core, except reverse. You're going from the pudding to the water, because you're going from water to pudding. So you speed up from the solid to the liquid and then slow back down again at the solid. And we can detect where these points occurred based on part of the energy reflecting and part of the energy refracting. We can pick up that data knowing what time the earthquake occurred and how fast these waves move. We can back calculate the depth that these refracted at, which allows us to build a picture. This is further confirmed or assisted by S waves. So S waves travel through solids, S solids. And because they cannot travel through liquids, instead of refracting or changing speed when they encounter the outer core, they will instead reflect off of that surface. So when they meet that surface, they'll reflect out and bounce back out at the crust, which leaves us with what we call the S-wave shadow zone. Because it can't pass through the liquid outer core, it's not going to reach the other end of the Earth. It's just going to bounce back out on nearly one full half of the Earth, and that's our shadow zone, is what it doesn't reach. So how did this all happen anyways? Well, about 10 to 15 billion years ago, we have the Big Bang, which is a giant exchange of energy which sends a ton of matter flying through the universe. And mind you, in space there's no air resistance, so everything just keeps flying at the same velocity that it got shot out at during the Big Bang, which is why you may have heard that our universe is currently expanding. It's because it's been expanding the whole time. It's been expanding at the same rate the whole time, and it's expanding right now. About 4.6 billion years ago, a nebula or a gas cloud slowly contracted under local force of gravity based on the masses of whatever was nearby, which formed our solar system. And you can think of our solar system almost like a giant toilet bowl that's being flushed with throwing a bunch of little pieces of sponge or something that floats and is sticky in there. And as they swirl around, around and around towards the center, as our solar system would be a very slow moving toilet flush. Those pieces of sponge or sticky clay or something like that would stick together and eventually form a little bit of a conglomerate, and that's what we called the proto-Earth. So it grew by gravitational contraction, so as those things hit each other, we're increasing our mass, which means that we're increasing our gravity, so it's all squishing towards the very center and increasing gravity with each mass increase. And as these things start to circle around and build, we end up with our common Earth that we have today, whereas our proto-Earth was mainly molten rock. And one day our sun will eventually run out of fuel for all of its reactions which combust, which create fire, which is the sun, the star. It will eventually run out of fuel for that, and it will explode and then sink back in on itself to form a white dwarf, and that is the final stages of our flush down the drain. And a white dwarf is basically like a small black hole. Now that's way, way, way in the future, but we are actively spinning around that center of the toilet bowl and actually very slowly sinking towards our sun. We won't have to worry about that. We, or likely any humans ever. So this is the origin of the concentric layering of the Earth, because it started with a smaller piece and built out from there and got bigger and bigger. And what we have from the center of the Earth and the escape of the heat is, remember that this started as a proto-Earth, mainly molten rock. So the way that this molten rock would escape the center is via volcanoes, just as they do today. The thing is that when heat escapes from the center of the Earth and out these volcanoes, it doesn't go back in. So all of Earth's heat that we have today, or the majority of it, is what we call ancient heat, left over from the original proto-Earth, as well as a little bit of heat that's generated from radioactive decay, but for the most part, ancient heat. When we lose this heat via volcanoes, it's not coming back. The heat that stays in there and stays in convection cells will stay, but eventually and over time, it's just slowly heat loss, heat loss, heat loss. So is the Earth warming or cooling? Well, that is kind of a hot topic right now, but it depends on what scale you're considering. If you think about the entire 4.6 billion year history of the Earth has cooled. It's gone from completely unlivable conditions, entirely molten rock, to frozen, essentially. And the window where humans or life can exist is very small on the much colder end. And so over 4.6 billion years, yes, the Earth is cooled, but if we were to make our timeline the last 200 years or so, and we're looking at just that small window of temperature where life is possible, we're actually seeing that it's warming when it at a much faster rate than it should be, based on a bunch of historical data that we have on our atmosphere. And that's something that we'll dive much deeper into later in the semester. We have a whole lab and lecture on climate change. So the answer to, is the Earth warming or cooling? It depends on what scale you're looking at. If you're concerned about the window of temperature where humans and other life can live and thrive and survive, it's warming, and that's on the order of about the last 200 years, immediately following the Industrial Revolution. And if you're considering the entire history of the Earth, well, it's cooled because we don't live in lava. So that's what I have for you on the interior of the Earth. Couple of quick reminders. You have a syllabus quiz coming up. I gave you guys a little over a week to do that, along with the online lab 1. We will be meeting in person next week for our first lab on minerals. Again, you will need your lab course pack for that. You can pick that up at KVCC's bookstore. If you're going to be on campus anyways for lab, you should just pick it up, get there a little early and pick it up. If you don't already have it, I will also be posting a lecture quiz for this, so I'll give you guys about a week to do that. Just a short 10-questioner. This is meant to A, make sure that you're watching the lecture videos, B, give me some feedback as to what I can do to improve these videos for you guys. but see as a study tool for you, because a lot of the questions that I put in these quizzes will repeat themselves in your exam. So you will only have one attempt to take this quiz, but I will set it to where you can print off your submission with the correct answers if you got any wrong. That way you can review those prior to test day. So that's everything. I hope that you guys are having a good week, and I will see you in the next lecture.